Yeah, thank you for this introduction. I'll begin with my today's presentation. And hello, everyone. Thank you for coming. And my name's Yu Hou. I'm from Yonsei University. And this is a joint work with Jin-Duk Park. And my supervisor is Professor Won-Yong Shin. And the title of our work is Collaborative Filtering Based on Diffusion Models, Unveiling the Potential of High-Order Connectivity. So for our topic is related to collaborative filtering based on diffusion models. And so our topic, we want to investigate the potential of using diffusion models for enhancing collaborative filtering. And for better understanding or for better presentation, firstly, I'll introduce some brief introduction to the collaborative filtering and the diffusion models. So start with collaborative filtering. Collaborative filtering is a method in recommendation system. And collaborative filtering is one recommend items to users based on the preferences of similar users or items. So for example, on the left figure, this is a user item bipartite graph, and this graph shows user consuming behavior, and this kind of information also can be represented by this user item interaction matrix. And in this matrix, each element means for certain user, whether there's a link with certain items or not. If there's a link, just denoted as 1. If there's no link, just denoted as 0. So as we can see, the first user and third user, they have similar consuming behavior, so it have a high probability to recommend this item to the third user, which has not been consumed yet. So this is a simple example for collaborative filtering. And then for diffusion model. Diffusion model is one of SOTA methods for generating high-quality data samples by refining its output iteratively. So diffusion model, you want to learn a diffusion process that generates the probability distribution of a given data set. So originally, diffusion model is used in image generation, and this figure is an example. So assume we have a clean image here. Diffusion model have a two-directional process. So start from left to right, this is a forward process. It will add in the Gaussian noise gradually. And then from right to left, it's a reverse process. And it will do denoising with a neural network iteratively until get the clean data. So this is a basic concept about diffusion models. Actually, so for the combination between diffusion model and collaborative filtering, there is an existing work which is called Diffrag. Diffrag is one of pioneer work in this area, diffusion model-based recommender system. So original diffusion model is used in image generation, so we can assume we replace the image with user item interactions. And the same with before, in the forward process, we can add in the noise gradually, and in the reverse process, we can do denoising with neural networks and to get the clean data. So this is a previous work, Diffrag. And in the previous work, for each target user, they mainly focus on its direct neighbor information. But actually, the multi-hop neighbor information also plays a very important role in collaborative filtering. So how can we fully leverage the power of multi-hop neighbors for capturing collaborative signals? In this slide, this is an example of the beneficial of using multi-hop neighbors for collaborative filtering. So the left one, this figure, this is a user item bipartite graph. As we can see, on one side, this is a set of users, and on the other side, it's a set of items. And they also have a connection between of them. And for each target user, we can find its high-order interactions by exploring its multi-hop neighbors along the paths in this bipartite graph. So on the right, here, this is an example of the high-order interactions for the user 1 and user 3. So for each user, as we can see here, for user 1, we can find the first hop, second hop, and third hop neighbors. And furthermore, For these two users, they have different direct user item interactions, but they share similar high-order interactions. So for recommendation, it have a high probability to recommend this item 1 and item 3 to user 3, and it's also we can recommend this item 4 to user 1. So this is the beneficial of using multi-home neighbors for CF. And our intention is under the diffusion model-based recommender system, we want to inject this multi-hop information into the learning model during the reverse process. Yeah, and how can this high-order connectivity be efficiently and effectively incorporated into the diffusion model-based recommender system? And we are facing these three challenges. So first challenge, that is how to encode this high-order interactions, or how to use a vector to represent this multi-hop neighbors, or how to use a vector to represent the graph structure. And the second challenge is how to maintain the complexity when including high-order connectivity. If we consider this high-order connectivity information, it will be naturally bring some actual computations. And for the third challenge, that is how to link this higher-order connectivity with the user item interactions under a diffusion model-based framework. That means how to link or how to merge the direct neighbors and the multi-hop neighbors information together. And our method, we want to solve these three challenges. And in this presentation, I will interchangeably use the term high-order connectivity and multi-hop neighbors. I want to express same thing. Yeah. So this is a schematic overview of our method, which is called CFDiff, when both 2-hop and 3-hop neighboring nodes are taken into account. Yeah, this figure looks a bit messy, so I'll explain this step by step. So firstly, same as before, given a user item interaction, in the forward process, we will add in the Gaussian noise gradually. And then, in the reverse process, we propose a learning module as our core module. We use this learning module to do denoising iteratively and to get the clean data. And our intention is we want to inject the high-order connectivity information into this learning module. Yeah, and also, as I mentioned, if we want to inject this information, it also will bring some actual computation. So before doing this, we consider using an autoencoder to project this information into a latent space. And in the latent space, we'll consider using a cross-attention mechanism to combine the information together. Yeah, so this is a schematic overview, and I'll give more details about this method. So firstly, how to encode this high-order interactions. And on the right, this is a general equation for H-hop neighbors encoding. I don't think I'll explain more details about this equation. For better understanding, here I give an example, which is easy to follow. So for example, still we have a user item bipartite graph, set of user and set of items, and they have a connection between them. And for target user, which is node 1, it will be straightforward to get its first hop neighbor. We can just use this binary vector to represent its first hop neighbor information. And based on its first hop neighbor, we can further explore its second hop neighbors along the passes in this bipartite graph. And then this node 2 and node 3 is selected. And then for each node, they have different number of links. So for each node, we also add a weight to this node related to the number of links. And we also use the same way we also can use this vector to represent its third hop neighbors. So we can use it this way to encode these high-order interactions. So this solves challenge 1. And also this high-order connectivity information is encoded in the pre-processing stage. So this encoded information is then fed into the learning model. So for the second challenge, that is how to maintain the complexity when including this high-order connectivity information. So here we consider using a hop-specific encoders project the user item interactions and high-order connectivities into a latent space. So that means this direct neighbors and multi-hop neighbors are compressed into a lower dimension latent space. And the latent space is much smaller than the original space. And we do further computation on this latent space. So the computation is related to how to merge them together. I'll explain that part in the next slide. So after that, we use a decoder to do reconstruction, and then we can get the next time step data. So using this way, we can solve this challenge 2. So this autoencoder structure can capture the high-level patterns of user item interactions and high-order connectivities information. And we can keep the computations manageable by controlling the latent dimension. So this is for challenge 2. And for the last challenge, that is how to link high-order connectivity with the user item interactions under a diffusion model framework. So in a word, we use a cross-attention mechanism. And here in this figure, we highlight one time step process. And here we can see there are two blocks. The top one is for merging the second hop neighbors, and the bottom one is for merging the third hop neighbors. And then the multi-hop neighbors can be viewed as a Q value, and direct neighbors can be viewed as a V and a key value. And then we can use this equation to do computations. So there is one thing we need to notice, that is this multi-hop and direct neighbor information are originating from the same user. And they offer two different perspectives of the same data. So we can use this cross-attention mechanism to merge them together. Okay. So by doing so, we can solve the third challenge. And this dual perspective is beneficial for capturing the collaborative signal by the cross-attention mechanism. Yeah, this is about methodology. And we also give a theoretical analysis. Here we show two theorems. So for the first theorem, because our cross-attention mechanism is happening in the latent space. So for the first theorem, what we want to say is we can control the hidden dimension to keep computations manageable while minimizing information loss from autoencoder. And for the second theorem, it's related to complexity analysis. So the conclusion is the model complexity scales linearly in terms of the maximum number between users and the number of items. So this is the end of methodology part. And then we do, I'll show some experimental results. We do the experiments on these 3 data sets. And for the benchmark method contains general benchmark method CF and also generative model-based CF. And we use this NDCG and recall as a performance matrix. So this is the overall experimental comparison with benchmark method, and nothing special. And here the bottom line is the maximum improvement rate is achieved about up to 7%. And for the second experiment, here we want to investigate the impact of multi-hop neighbors. So in this experiment, we tune the hyperparameter H, which is related to how many hop neighbors were taken into account. So for each data set, this CF div H, that means constantly considers up to H hop neighbors. And from the table, we can see incorporating a wider range of neighbors can positively influence the recommendation results. And there is a decline in the performance axis of certain hop neighbors because of noises. And for the third experiment, it's about the validation of computational complexity. And for this experiment, we do this on synthetic data set. So in these 2 figures, x-axis is the number of users or the number of items, and the y-axis is acquisition time. So the conclusion is that the model complexity scales linearly with the maximum between the number of users and items, which is also confirmed our second theorem. And I'll conclude today's presentation with these takeaways. So our method, CFDiff, is the first attempt to utilize multi-hop neighbors in diffusion model-based CF. And the proposed learning model incorporates a high-order connectivity information through a cross-attention mechanism while keeping the model's complexity at a manageable level. And we validate the theoretical scalability and the computational efficiency of CF. I think that's all. Thank you for listening. If you have any questions, feel free to ask. Yeah, thank you.